Next, please allow me to welcome paper ID 423, Gabriel Coutrin from University Center of FEI, Brazil. Gabriel Coutrin is a graduate student of Image and Signal Processing at the Department of Electronical Engineering of the Technical University of FEI, Brazil. His ongoing research work is about automatic classification of newborn pain assessment using face images. It is a collaboration with the Federal University of São Paulo of Brazil. The speech title is Convolutional Neural Networks for Newborn Pain Assessment Using Face Images, a quantitative and qualitative comparison. Dr. Gabriel.
Hello, everyone. Can you hear me?
Yes, I can hear you.
Okay, let me share my screen.
Okay.
That is the one. Yes. Can you see my screen?
No, I can't. Oh, yes, I can see you now.
Okay, so let's start. Well, hello, everyone. My name is Gabriel, and on behalf of all my co-authors, I'm glad to present our work, which is the convolutional neural networks for pain assessment, for newborn pain assessment, using face images, a quantitative and qualitative comparison. Here's the outline of the presentation, and I'll start with a brief introduction to the topic. So the pain experience, when intense or repetitive, may harm the development of newborns. Several clinical and non-clinical studies have been carried out to identify the presence of pain through behavioral analysis, mainly by facial expressions. Computer science have proposed automatic frameworks based on facial expressions that are specific to the pain phenomena and enable continuous monitoring of the neonate. In this context, we implement and compare several state-of-the-art convolutional neural networks, evaluating their performance based not only on quantitative, but also qualitative analysis, using explainable AI methods. So in order to train these models for neonatal pain assessment, we used the following data sets. The first one is the ICOPE, the infant classification of pain expression. It has 200 images from 26 neonates. And the UniFesp, that is the Federal University of São Paulo dataset, it has 360 images from 30 neonates. And for both the datasets, we cropped the newborn faces using the face detector retina face. Because of the lack of images, we applied the transfer learn technique in order to use the state-of-the-art architectures. In other words, we selected some CNNs that were trained for different tasks and performed a new training or for neonatal pain assessment. Specifically, we selected a VGG16, a HESNET 50, and a squeeze and excitation HESNET, that is the HESNET CNN with some squeeze and excitation attention modules. And those three CNNs were originally trained for face recognition. We also selected an Inception V3 model trained on the ImageNet dataset, since we haven't found a version trained for face recognition. And for each pre-trained model, we proposed a new set of fully connected layers, as it is shown on table 1. In addition to these 4 well-known CNNs, we also implemented the neonatal convolutional neural network, or the NCNN. That is the first CNN developed specifically to the classification of newborn face images. It was proposed by Zanzi and Associates in 2019, and on its original publication, the NCNN achieved an accuracy of 91% on a private dataset, the NPAD dataset. And since there is no pre-trained version of this model available online, we had to rebuild it from scratch, following the original description provided by the paper. All the CNNs were trained and tested using the following protocol, which we are calling the leave some subjects out. And actually, that is a k-fold cross-validation at subject level. So by uniting the 2 datasets, we had a total of 56 subjects divided into 10 folds, each one containing 5 to 6 subjects, and 3 are always from UNIFESP in order to maintain the balance within the folds. And this strategy avoids data leakage since we won't have images of the same neonate in both test and training sets at the same time, and also guarantees more images for testing when compared to the classic leave one subject out. In each iteration of the cross-validation process, we applied the data augmentation technique only on the training set, in which we generated 20 new samples per face image. And each new sample was verified by the face detector retina face, and only the valid images were indeed used for training the models. XAI techniques are able to explain decision-making process that leads an AI model to a particular answer. This work selected the gradient technique to perform the qualitative analysis. So the gradient, that is the gradient weighted class activation mapping, use class-specific gradient information to localize important regions in image. It produces an attribution mask by evaluating the gradients between a convolutional layer and the desired output. So in other words, the gradient is capable of producing a heat map that indicates the region of the image that are important to the model's prediction. And now let's take a look at our results, starting by the quantitative analysis actually. I mean the evaluation metrics. So as you can see on table 2, the VGG, the HasNet, and the SqueezeNet models presented a similar performance and outperformed the Inception V3 and the NCNN. Those 3 models achieved more than 85% level for all the evaluation metrics, and there is no statistical difference between their results. However, VGG has overall the fastest convergence training process. I mean, it needed less epochs to converge. And for all the CNNs, we observed a high standard deviation for all the metrics, showing the sensitiveness to the training test samples chosen. And now to illustrate the qualitative analysis, I'm presenting here some samples of the correct classification for each model. So we have 2 samples from the ICOPE dataset and 2 from the UNIFESP. And now thanks to the gradient heat map, we are capable of solving the tie presented by the evaluation metrics. I mean, now we can distinguish the behavior of VGG, HasNet, and squeeze and excitation net. So apparently VGG 16 associates the non-pain state with the nose in the region between eyebrows. And when pain is detected, it also highlights the forehead and the nasolabial furrows of the baby. It's important to notice that these facial features are actually used by neonatologists when they perform this kind of assessment, this pain assessment. And so this is a surprising result to notice that this model has some similarity with the action of experts. On the other hand, the HasNet and the SqueezeNet models presented a similar behavior. They both seem to use the entire face in the decision process as a holistic view of the face. However, this approach makes it difficult to identify the relation between classes and facial features. Thus, we can say that VGG has a better explainability. It's easier to justify its decisions. Regarding the other models, Inception V3 is capable of recognizing face elements, as we can see on these examples. However, its attention is easily drawn by external objects, such as the second sample. There's a ball, and the heat map is all focused on the baby's ball. It also seems to associate the pain state with the open mouth. And because of the attention fact, they're easily drawn by external objects, we cannot rely this model. Inception V3 is not reliable to the desired task. And at last, the NCNN, it also seems to associate the pain state with open mouth, the open eyes with the no pain state. However, its activation maps usually have a scattered behavior, and this intensifies when the open mouth or the open eyes are not present on the image. So it's difficult to identify any pattern of facial expression analysis. It seems that the model didn't learn the task properly. And we hypothesized that one possible cause of this difference between the model's performance is the original training of each one. So the top 3 CNNs, the VGG, HasNet, and SqueezeNet, were all trained for face recognition, were all trained for face images, that is a data type similar to ICOPE and UniFASP datasets, while the Inception V3 was trained to distinguish the 1000 classes of ImageNet. So it probably doesn't know how to extract specific facial features. In ours, NCNN had no prior training, had no prior knowledge. And the ICOPE, the UniFASP datasets were certainly not enough to train this model from scratch. We couldn't exploit its full potential. Our work described the systematic and detailed comparison of several CNNs when performing neonatal pain assessment. Our quantitative results show the superiority of the models that were previously trained on face images. By applying the gradient technique, it was possible to distinguish these models qualitatively as well. In this context, under the conditions of the present work, the proposed VGG16 model is the best suited for neonatal pain assessment because it presents high performance and explainability, since there's some agreement with the neonatologists. And it's important to notice that the lack of images is a limiting factor for the application of deep learning in general in neonatal pain assessment. Besides data protection policies, the very nature of this studied task represents an obstacle for data collection, since pay-for procedures imply ethical issues. Another drawback is the lack of standardizations of data sets. And as future work, our ultimate goal is to develop a CNN that during training also considers the human knowledge. To accomplish this, we will use the visual cognitive perception of experts performing neonatal pain assessment through facial expression. We believe that the combination of prior knowledge from experts with the current state-of-the-art CNN models may enable even better performance and specificity to the pain assessment, overcoming the limited training sample problem in the subjective of the human judgment as well. Thank you so much for your attention, and thank you, Mike Ed, for this opportunity. And please feel free to contact us if you have any questions regarding our work. Thank you.
Thank you, Gabriel. Thank you for your excellent speech.
Thanks.
If anybody have any questions for Gabriel. No? Okay, let's thank you, Gabriel. Goodbye.
Thank you, bye-bye.
Bye-bye.